So the Michelson-Morley experiment concludes that as far as we can tell, there is no ether. As far as we can tell. And then I had said in an earlier lecture that there were other things that have happened since the 1920s when this was happening, or the 1910s when this was happening. And Michelson-Morley was 1887, and then Einstein came along in 1905, and then people looked more closely at this. Right? Einstein said in 1905 that C didn't have a frame of reference, but things have been done since then that have definitely shown that there is no preferred frame of reference for light, there is no ether. So we've got, remember, postulate 1 for physics is all physics should be the same in all inertial reference frames. Physical laws should be the same in all inertial reference frames. And now postulate 2 that Einstein adds in order to do our mechanics, our physics. He says that C is independent of frame of reference. So in order to conclude that C is independent of frame of reference, Einstein also has to conclude that the Galilean transformation is incorrect. Therefore, the Galilean transformation is incorrect. And is it so incorrect that we have to throw it away? No. This is what you've got to realize about us improving science. It's not so incorrect that we have to throw it away. It's just incorrect in a certain realm. It's an approximation. And it's an excellent approximation for things that are going at speeds much, much less than c. But once we start dealing with velocities that are approximately equal to the speed of light, we need new physics. And that's Einstein's physics. And that's Einstein's special relativity and general relativity. We are going to do special relativity here. So I'm going to start with special relativity by showing an extremely important result of postulate 2, that C is independent of frame of reference. And then we will do some derivations to show what the replacement for the Galilean transformation is. So the first thing is there's what's called Einstein's thought experiment, or Gedanken experiment. Gedanken is a thought experiment. A Gedanken experiment is one which you can imagine. You could imagine as you could do. You can certainly see that the physics is good, but it's actually in practice it would be impossible to do. So let's do this Einstein's thought experiment. In order to explain the results of c, the speed of light, being independent of frame of reference, Einstein talked about this experiment. If you have two train cars, and you have Frank and Mary are on the two train cars. So Frank is standing in the center of one train car, and Mary is standing in the center of the other train car. Guess I need to give them both arms. There we go. Okay, now they're good enough people, right? Let's make Mary a moving reference frame, moving at speed v, so she's going to be O prime, and Frank is in the O frame of reference, Frank and Mary. Okay, let's just say that lightning strikes. One of the things that is not obvious here, Frank and Mary are on two parallel tracks, right? They're really close to each other. Let's say that lightning strikes both ends of Frank's car at the exact same time. Lightning strikes both ends of Frank's car at the exact same time. Okay. Doesn't matter that lightning, whatever, doesn't matter. So lightning strikes both ends of Frank's car at the exact same time. How does Frank know that lightning struck at the exact same time? Frank is not standing where the lightning struck. So how does he know? Right? If he's standing in the center of the car and lightning strikes either end at the same time, how does he know that it struck at the same time? He knows because he can time the amount of time it takes the light to get to him from the lightning on the right, and the light to get to him from the lightning on the left. And he can say, I can say that delta t, the time between the amount of time I saw the lightning strike on the right and the lightning strike on the left, is 0. They happen simultaneously. That's what delta t equals 0. It happens simultaneously. In this case, where that's the difference in time between two events. In special relativity, we often talk about two events. Event 1, lightning strikes the right of Frank's car. Event 2, lightning strikes the left of Frank's car. The time difference between those two events is 0. How does Frank know that? Because the light arrived at his eyes, right? It struck the car, and then it went to his eyes, and it took the same amount of time to get to his eyes from either side. Okay, so what would Mary say? Let's say that Mary's train car, which is really close to Frank's train car on a parallel track, is traveling by Frank's stationary train car, and she's traveling at speed v. And at the moment that the lightning strikes, let's just say at the moment the lightning strikes, Mary's car is is in the same place as Frank's car. But now, given that it takes time for the light to get from the point where it struck, those black lines, it takes time for the light to travel. In that amount of time, Mary's car has moved to the right, right? Mary's car has moved to the right. By the time that Frank sees the light, Mary's car must have moved to the right, which I'm showing here. And that means that Mary must have seen the light from the front of Frank's car before, right, she sees the light from the back of Frank's car, because she's going to meet that light coming from the front of the car, right, before it gets to Frank's eyes. And the light coming from the back of the car has farther to go now, and so she is going to see the light from the front of the car before she sees the light from the back of the car. This is true. This is correct. There's nothing wrong with this physics. She's going to see the light from the front of the car before she sees the light from the back of the car. And you say, okay, that's fine. That's what the Galilean transformation tells us. But there is no Galilean transformation. Mary still has to say, right, because the lightning struck the front of Frank's car when Mary's front was parallel to Frank's front, Mary has to say that the light coming from the front of the car took less time than the light coming from the back of the car. But because the light, as far as she's concerned, it's the same as if it was coming from the front of her car, because the front of her car was in the same place as the front of Frank's car when the lightning struck. She's moving. She sees the light before Frank sees the light. So what does she have to? I'm sorry. She sees the light before Frank sees the light, but she sees the front light coming from the right or the front of the car before she sees the light coming from the back or the left of the car. So what does she have to conclude? If the light is still coming at her at C, then she can't conclude just that, oh, the light from the front came at me faster. She's in the center of the car. She has to conclude that T2 minus T1 is not 0. In her frame of reference, T2 prime minus T1 prime is not 0. She has to conclude that whoops, I got that backwards. Not true, I didn't get that backwards. I didn't get anything backwards. I just said it's not 0. She has to conclude that light on the front of the light hit the front of the car before it hit the back of the car. So she concludes delta T prime is not equal to 0. She has to conclude that the two things did not happen simultaneously. So this is the result of postulate 2. The result of postulate 2 is if two things are simultaneous in one frame of reference, they are not necessarily simultaneous in the other frame of reference. Actually, what the result really is more general is that a time measured between two events in one reference frame is not necessarily equal to the time measured between two events in another reference frame. Time is no longer absolute. So what Einstein concludes from this Gedanken experiment is that time is not absolute, that the time measured between two events in one frame is not equal to the time measured between two events in another frame. And let's go ahead and derive and see how that is, how that comes out in equations.